we are talking about lighting model in OpenGL. So, lighting is one of the principal part in OpenGL, like texturing, or we have vertex transformation. Lighting is also highly important. It makes a kind of a scene realistic, like people feel that model is illuminated in a light source. So lighting is important in OpenGL. When we see lighting, there are three components in the light. One is light source that emits the light. Material, actually we are looking the material, not the light. So light source, material, and then our eye. Our eye watches material. Light falls on material. Material reflects the light and it comes to our eye. To get better illumination, light must fall on the surface in perpendicular way. If light and surface are parallel to each other, then surface won't be visible nicely. If light falls on surface at 90 degrees, then surface would be illuminated to its maximum strength. So, light source falling at what angle on the surface, and surface is at what angle to the eye. Light has three parts: its position, its direction, and its color. Okay. So in lighting model, when we talk about the light, material, and camera eye, then for the light we talk about its position. So light may be at infinite far away, like sun, or light can be nearby, like bulb light or candle light. So that is called a positional light. So type of the light: light position, light direction. In what direction light is to the surface? So we don't call it that light should fall on the 90 degree at the surface. So every surface has its normal. So light should be in parallel to the normal. In mathematics, light direction and normal, if we make dot, then it should be 1. So that is the idea. Now when light reflects from the material, it falls on our eye. So three things in light model: light position, light direction, and color. Okay. So position can be infinite away, position can be nearby, positional light. Light direction, light must be in direction from at the normal of the material. And light color. So light falls on material, material reflects the light, and reflection should come to our eye. It should be in this position. Now, once we talk about light, color, and material reflection. So material should, if material, the nature of the material reflects the color, what it is. If material is green, then it reflects green color. If material is blue, it reflects blue color. If material is mixture of green and blue, so that one it reflects. So let's consider material is green, then it reflects green. Light must have green. If light is red, then material has nothing to reflect from the light. So if light is red, falls on a green material has nothing to, it absorbs the red light and it tries to reflect green, which it doesn't have. So it looks black. So if I have a white light that has red, green, blue, all three, then green material would absorb red and blue and it would reflect green. And it falls on our eye and we look at it look green. So that is the concept of coloring. So three things as we talk: position of the light, direction of the light. Direction of the light, it should fall directly on the material in the sense that it should fall at the 90 degree at the material, or should be parallel to the normal at the material, and material should reflect the light. Once it reflects the light, then it should fall on the camera. Okay. Now be more realistic in the OpenGL. OpenGL is like in the smooth shading model. OpenGL is like a vertex manipulation. OpenGL doesn't think much about all the pixels and light falling at which pixel and light not falling at which pixel, color at which pixel. So this computation doesn't happen in OpenGL. All calculation happens for the vertex. If I have a triangle and in the triangle I have 3 vertices, calculation will happen at 3 vertices only, not the thousands of pixels in between. So if light position matters from the vertices, light direction matters from the vertices, reflection happens from the vertices, and then it falls on our eye. So whatever computation we make, then that computation finally comes to the pixel. That is called fragmentation or rasterization. So in OpenGL we provide vertex coordinates, we provide vertex color, but in lighting model we take away the coloring. We provide material properties like ambient or diffuse, like a specular. So these are the property that we provide. So main property is diffuse property. So if we provide diffuse color at the vertices, that is the color. So light, once it falls on the vertices, then vertices reflects its diffuse property light and it falls on it. So 2 things we talked about. One is general concept of a light, like its position and its direction and its color. This is the general tradition. If a ball is green, light must have green component. Light must fall on the ball and in the direction, and ball must reflect the green component to the eye. So this is normal tradition. In OpenGL, we have to consider only vertices. So what is the vertices normal? So that light should be in parallel to the normal, and when it reflects, where is the camera? So in OpenGL, we take care about the vertices. Next thing what we take care in OpenGL is model view matrix. So we have three matrices: projection matrix, model matrix, and view matrix. So what do we see? That the model must be inside the projection box, and from a view perspective, generally we keep the view fixed. So if model has a transformation, then finally we see from the view or from the eye what is the final transformation, and that we try to show it. So model inside the projection box comes to the view. What about lighting? What about the light source? If light source light position is declared after the model view matrix is defined, then it follows the transformation. So we can also rotate the light source, we can also translate the light source like this. So 2 things special. One thing we talked about natural lighting, that is position, direction and color of lighting. Material reflects a particular component of color, it falls on camera or eye, that is the natural. In OpenGL, whatever computation we do, we provide vertices, we provide normal, we provide coloring of the vertices through diffuse. So vertices computation happens in OpenGL. And next is that light is also subject to transformation. It can also rotate, it can also translate. If position is defined, position is placed in the source code. After we load the model view matrix, after we place identity matrix, then it is also subject to transformation. If it is before it, then light source is fixed. If it is after, means if it is along with the model and we start translating or doing the transformation, then it would also transform. If we don't want transformation, it should be declared before the view matrix is declared. Okay. If we declare the light source after the view matrix and before any transformation, it won't transform. It will be static. As we keep any one. So this is the lighting modeling. Okay. So we'll see through further how it is.
In continuous OpenGL fixed function pipeline. So we'll proceed and test. This is Linux Mint. We'll proceed point by point. OpenGL lighting model. Lighting model is important everywhere. So we'll see lighting model that is implemented in OpenGL, and it's feasible, it's workable. So what is the mathematics behind the scene that we'd see? OpenGL lighting model constitute light source, mainly RGB we'll talk about, material reflecting light RGB to the eye. So light source and material. So OpenGL in lighting model, it supports RGB and color index. So we'll discuss about RGB. For GL smooth shading model, only this is what we are talking now. And vertex has to receive the lighting. Vertex has to receive the lighting. No explicit per fragment pixel calculation. Means lighting calculation has to happen at the vertex. Kind of a fragment shader in the shader. But anyway, we are not discussing about shaders now. Light source position set after view matrix is subject to transformation. So if light source is set after view matrix, then like a model is transformed, rotated, scaled and translated. So light source can also be rotated, translated in that manner if it is position is set after view matrix is set. Light reaching to the eye or camera depend upon the light source property, like what is position, direction and color. So these three things are important things. And this is, it follows transformation if it is declared position is set after the view matrix. For the GL smooth shading model, vertex has to receive the lighting. And RGB light is emitting RGB color, material reflecting RGB to the eye, and it supports RGB and color index model. So RGB that we'll see. Okay, so we'll see lighting type. There are two types of lighting. One is directional light and one is positional light. Directional light is a light that is kept infinite away. Like here, it is kept in plus z direction, infinite. So the light that comes is parallel. So shadows are parallel. Light comes from infinite distance. Like here, this is plus z axis and this is minus z axis. So light is going towards minus z axis from plus z axis from infinite distance. There is no position here. I cannot say that light is kind of this is the starting point. So there is no position. So from infinite position in z direction, it is going in minus z direction. So this is directional light, whereas positional light or point light, is also called point light. So point light, it is placed at one location and kind of in 360 degree, the way any light is, like a bulb, that it emits light in all direction. So in 3D all direction. So light is kept at a position. So this is a position. This is a position, and around it light is being emitted. This is positional light. Whereas this is directional light. It is coming from infinite point to a direction, minus z direction, and parallel lights. Certainly this is not a parallel light. Okay, so light source can be made a spotlight by placing a cone. Like if I have a positional light and I am placing a cone. So this is one side of the cone and this is another side of the cone. Okay. So this is one side of the cone and this is another side of the cone. So this is a cone. Light that is inside the cone, that only propagate, otherwise these areas there is no lighting. So this is called spotlight. So spotlight is also famous, means also possible, I would say. So this is parallel light, directional light, point light, positional light. If I place a cone, I can make it as a spotlight. So I have to set some property and it becomes a spotlight. I have to mention the angle in the spotlight. Okay, so as discussed, if I have like this is a pyramid, one side, next side, and this side. This is the base. This is a pyramid. For the pyramid, these are the vertices. This is a vertex, this is a vertex, and this is a vertex. This is a vertex. Light must fall on the vertex. Light may not fall on the surfaces. Not required. So, vertex, if we see without lighting, we specify the vertex coordinate and vertex color. Instead of vertex color, now it will come as material properties. So, light must fall at the vertex. Whatever the light color falls at the vertex and whatever the property of the material is, that point will carry that light. Then it will span over all the area in the surface. So, in a smooth model, if this is red and this is green, then in between this area would be yellow. So light must fall on the vertex. This is a big point. Light position for the directional light in the direction. Okay. So in directional light, if I set light position, so position of a light, this is 0, 0, 1, 0. Okay. Whereas for the positional light, this light position, so positional light, if I set light position 0.8, 0.2, minus 1.2, that is the position of the light, not the direction. If I set the fourth parameter as 1, so this becomes a positional light. So whatever the coordinate I am setting, these coordinates are position of the light, and light would be is kind of omnidirectional. In all directions it would propagate. But if it is a directional light, last parameter would be 0, argument would be 0. So claiming it is a directional light, and whatever we are placing 0, 0, 1, it shows that direction of the light. So 0, 0 means x is 0, y is 0, z is 1. This is 0, 0, 0 origin. This is the direction we are talking about. 0, 0, 1. This is z is 1. in this direction at infinite distance, light is placed. Okay. So, if I say light position is 1, 1 and 0, means x is 1, y is 1 and z is 0. So, it is positioned in xy plane, that is 45 degree in xy plane. So, that would be in this direction. So, if I say okay, so this is the origin and this is z axis. Okay. Now, if I say light position is is 0, 1, 1, 0. So, fourth parameter say is a directional light. So, 1, 1. So, if I see the vector, then, okay, if I see the vector, then this is 1 x-axis in this direction, one y-axis in this direction, both are 1, means it will go in 45 degree from x-axis and y-axis. So, light is in this direction and the angle is this. So, this angle is 45 degree. Okay, so since it is a directional light, so light in this direction, light is actually it is placed somewhere far infinite in this direction. So actually light is coming in this direction. If light position says 1, 1, 0, 0, 1, 1 is this, z is 0. At infinite distance, light is placed. Since light is placed here, it is pointing in reverse direction. So, in this direction. So, this is directional light source. So, if I say light position in 1, so somewhere on z axis light is placed. Since light is placed at infinite distance, light is pointing in this direction. Whereas in positional light, whatever the position we are setting, light is positioned at that direction and omni way it is just emitting the light. Okay, so what is light emission and reflection? So this is a lighthouse and it has a color called 111. So it is kind of emitting a white light. So this is a white light. R is 111. Now, this is light emission from the light source and this is a model. This model has a color is 010, so red green, so it has a green. What it does is it absorbs red and blue. Since it doesn't has a red, it doesn't has a red and blue component. So R and B gone. G has 1.1, so it reflects green. This guy, since it does not have blue, and red, so whatever blue and red component comes, it reflects. So whatever blue and red component comes, it absorbs, and green it reflects. So even though the light coming is white light, only green is coming out. We can set this as 0.5. Then green will green will come out, but intensity would be less. We can come to a formula in this. Okay, so the formula would be for this is L light red into material red plus light blue light green into material green plus light blue into material blue. So this is the actual reflectance. This is the reflectance formula what this material support. So light is 1, light red is 1, material red is 0. So no lighting, no red. Light blue and material blue, same way material blue is 0. So there is nothing. Okay, so light and material, so only this part LG and MG, light green and material green, this is only will come into the picture. That's why it looks green. Okay, now it is 1 into 1, this is 1 and this is 1, so it would really look green. Here it is 0.5, though it is green, but intensity would be less. So this is the mathematical calculation for the lighting. So the material color reflects its light, absorbs other part. Okay, if light coming is red, no green and blue, then there would not be any lighting at all, because LR is 1 and LB is 1. Sorry, light is red, LR is red, LG and LB are 0, means these are 0, and MR is 0, so there won't be any lighting at all. So this is mathematical formula of lighting. In physical way, material reflects its color, absorbs other color. Lighting means in addition to RGB color, lighting has other component also. So if it is a if light is coming from a light source, it has ambient part, it has diffuse part, it has a specular part, and in similar fashion, in material also there is a diffuse part, specular part, shiny, specular, shining is part of a specular, and ambient. Okay, so ambience is kind of environmental light. Suppose there is no lighting. Suppose there is no lighting. If there is no lighting, then what would be the light of the material? Okay, so I am inside a room and there is no direct lighting. Lighting are through reflections from here and there and whatsoever. What would be the ambience lighting? So light source can add to ambience. And there is another guy called light model. Light model also adds to ambience. So ambience factor is a light that a material would show if there is no lighting. So that is the ambience light. Like here, this is the front light, but back side there is no lighting. So whatever we see, I think it's a kind of a greenish black. It's not pure black. It's a greenish black. So this is the light on back side. It is showing if there is no lighting. This lighting is depend upon the light model. Light model is another entity that we can add, we cannot add. It is up to us. So if we enable light model, and light model, if we change the ambience, so light model light model is available, and light model we can kind of add in, light model add or delete in the sense that ambience of the light model we can change. So if by default ambience of a light model is something, I think 0.02. So light model ambient and ambient of the lighthouse and ambient of the this material, all three comes to make a ambience of the material. Likewise, diffuse, likewise specular. So diffuse is the actual color of the light. Ambient is the color of the environment, the way the name is ambience. If there is no lighting, like backside of, typically if we have a lighting, what would be the backside lighting when there is no lighting? That is the ambience. Diffuse is the front light. What is the actual light that is thrown from the light source? So similar diffuse, so these are reflectance. If actual light is coming, so whatever we talk now, this is diffuse one. Whatever we see, it is diffuse light. So lighting is actually diffuse light. Out of all the lighting component, what we talk is light coming from a light source is diffuse light. Ambience make important if other side of the area in the material where light doesn't come, it should still show some color. This is the main light, diffuse light. Specular light is the place where light falls at 90 degree of the surface or in the parallel to the normal. There should be shining also. So that is called a specular component. All component follows this principle only, RGB, and this multiplication, all component. So these are different component of the lighting. Ambient, what would be the lighting of the material where there is no lighting. Diffuse is the actual light, and specular is the where the light falls directly, like here. Light falls directly at this part. So here there will be shining. Otherwise it will be like this. What would be the specular component? What would be the shining color? And what is the color shining color that is coming from the light source? So that also we can define. So light source is saying that if I fall directly on the material, then it should shine like this. Well, this is the OpenGL calculation method. Ambience makes sense, and diffuse also makes sense, but light source also identify that if light falls on material, then please calculate through specular component. And material also, so generally it is white because shining will be white. So that is the idea. So light has three component: ambient, diffuse, and specular. Ambient is if there is no light, then what the calculation will be. Diffuse is the actual light, and if light falls directly on the surface, what would be its shining color? So these are light component, and these are materials reflectance component. How much it would reflect? Like in this example, it is reflecting what, only 0.5. It is reflecting green, but only 0.5. Here it is reflecting green and full. So material, whatever material we have, all are reflectance kind, all are reflectance parameter. Whatever we have in the line, that is the actual light parameter. These two will get multiplied and in the direction of the camera eye. Finally, it will come to the actual lighting. Light follows model view transformation matrix. Like if camera is here and 0, 0 camera is here. Okay, so I think we can add. So if camera is here, Okay. If camera is here and we can see this model is placed, it is placed inside a projection box, and if light is position is defined after the light model position declared after model view transformation matrix load identity. Once we load the identity, then it is subject to transformation. If light is here, now light is here, that's it. Light can move the way model moves, the way model translate, rotate, and so the scale. So scaling cannot happen, but translate and rotate whatever we see, so that it can also follow. So this is the transformation. This is the transformation, means light also follows if it is position is defined after the view matrix and load identity is calculated. So this is about lighting. Okay. So there is a mathematics. So what would be the actual color at the vertices? So we said that the lighting calculation happens at vertices. So what would be if light has ambient, diffuse and specular? If light model has ambient and material has these many reflectance, what would be the actual color at the vertex? Material has also one part called emission, material emission, like what light it emits, like a kind of a light source. But it won't be that much bright, but its own brightness. So vertex color would be the material's emission. Ambience, light model into ambience material, like this, whatever calculation we made. LR, MR, and so whatever is ambience at the light model and material model. So this RGB. So ambience of the light model. So light model is external light, we can say. This is light source. This is light model. Light model is kind of external source. It has many other properties also. So what is the model of the light? So model of the light also adds ambience. Okay, but it would be in this formula only. So instead of LR, I can say LMR and MR. So the emission property of the material, the ambience of the light model into ambience of the model material. So if I set ambience of the light source to 0, still there will be ambience because light model ambience is there. This is attenuation. Light can decrease as per the distance. A spotlight effect, if we place a cone in front of the light, then depend upon the cutoff angle, the spotlight effect. Now ambience of the light into ambience of the material. Diffuse of the light, diffuse into the material. A specular of the light, a specular of the material. All factors if we add, plus, then plus. Okay. Okay. So this is the multiplying factor inside this. So again plus. So the ambience of the light, ambience factor, diffuse factor and shininess factor, whatever we get after addition, we have to multiply with the spotlight effect and the attenuation plus this, and then it becomes the okay. Now we can see there is a summation. This is number of the light sources. So if more number of light sources are there, then everything would get sum up. Okay. So in diffuse, this is L, means light, direction and normal. So we have to do dot. product, and similar to a specular component and the normal, we have to do dot. So light would be the brightest if dot means cos theta, cos angle. So cosine is maximum at the 0 degree. So normal of the material and light shows the light source direction. So it should be in the same direction. Means the dot should be 1. So it should be maximum. So material must be in material surface should be in perpendicular to the light, or material's normal should be parallel to the light. So this is the calculation. So we'll have lab session for all the calculations one by one, how it looks by changing what calculation. So it's pretty straightforward. Emission of the material, emission of the light model and material. Now for each light source, I equal to 0 to n number of light source, attenuation, a spotlight effect multiplied by all these factors, ambient, diffuse and shininess. For each we have to add, and that would become the vertex light. Means that would be the light that reaches the eye. Okay, so we have okay, so that is the material, that reaches to the camera. So finally the light should reach to the camera. So this, after adding this, if it crosses 1 means light has a boundary 1.0 in a float, then it would be kind of it would be curtailed to 1. So there is a boundary. So this is the idea. Now we demonstrated in. Now we will have a lab session. So in lab session, first we will go with the light source type, then light model, emission and ambience, diffusive and specular, then a spotlight. So this is the lab session we have kept for this. So in the current lab session, that is the first one, light source type. This one light source type. So this is the actual model of the lighting. So we can see that this is the camera, and camera is pointed towards minus z axis. This is the projection matrix, and inside the projection matrix we have a sphere, we have pyramid, and this projection is we can make it ortho or perspective, whatever comes to our need, and it so far of the projection is 10, near is 1. This is our lab session, and minus 0.5 will place the local coordinate. At the local coordinate we draw these models, and from the local coordinate 1.5 distance we will have the light source. So this is the setup. So if I set 1.5 as a light source position in z direction, this would be the light source for the positional, whereas for the directional it would be infinite plus. It doesn't matter 1.5 or 4, it will be in z direction, and at infinite location the light source would be kept. So for the directional light, if I say the light position is 0, 0, 0, 0, 0, 1.5, light will be placed on 1.5, that is z axis, somewhere in the infinitely away, that is directional light, and this for the positional light it would be 1.5, it would be distance from the local coordinate, and so we'll show the directional light and positional light. Then we'll show the transformation, color emission, smooth shade model. Okay, so if it is a directional light, then light coming from the, so this is a perspective projection. So coming from the z axis, so this is the light source, but for directional this is far away, and we have a pyramid and we have a sphere. But if this is the positional light, then you can see that emission, its ambience is seen, because light is here. Because light is here. Since light is here, then it would behave like this. This part of the sphere is visible, this part is not visible. But here, in directional, light is coming from the infinite, here, from here. Light is going. So it would show like this. You can see shining is almost at the middle, because this is the perspective. In ortho, it will be exactly at the middle. So we have taken example from the ortho, from the perspective projection. In ortho projection, it will be exactly in the middle. That we will see. And light is seen from the infinite source. It is both are shining, we can see. But since this is a positional and we have only limited vertices, one vertex is here and one vertex is here, and one vertex is here and one vertex is here, and one vertex is backside. So we can see only blue, because the color of this vertex is blue. These vertexes are not getting the light. So like this, it is red and it is green. But since it is positional near to the model, only this vertex is getting enough light. These vertexes are far and they are not getting the light. So light must reach the vertex. That is the idea. And from the right side, it is coming to this area. Back side is only ambience. So we have set ambience as blue. Okay. So this is the position and direction and type of the light. Now transformation, light can be rotated. Light is above now. It's possible, and it is showing the light from the top, like I have a chair. Okay. Color emission. So color emission and reflectance. So light does not have, light color is red and material color is green. So there is no color. Whatever color we are seeing is ambience color, because light model has white light. So it multiplies with the ambience of the material, and that comes to blue. So that we can see potentially there is nothing green here. So light is red, material is green, so there is no lighting, because there is no calculation, it's 0. Light intensity test will make like this is light, this is kind of bright light. So light also intensity we can change. It is a low bright light. And a smooth shade model. We can see that if camera is placed here, then light is everywhere. Or I can say if light source is placed as a directional, I can say this is a directional everywhere. But if light source is near somewhere and no vertex is receiving the light, then there is no light. This is positional light we have placed somewhere center, so that no vertex should receive the light. So vertex must receive the light. So this is the lab session that we will do. Okay, so we'll proceed with the writing the code. We'll create a directory. Dir OpenGL light. Okay, so it is empty directory. Okay, so we'll have a file that is gllight.py. From OpenGL.gl import star. Here you import star from OpenGL.glut import star. Now we'll import RE. I have a library file that is OpenGL utility, and it contains shapes, different shapes. Okay, so here we are. So from OpenGL, we will copy this file later. OpenGL util import pyramid util C and shape. Shapes will initialize how many shapes we support. So in shapes, first we will have a light cube. That light cube is a cube that show the cube where the light is. This is light cube. This is light cube. This is light cube. This is light cube. So light cube will show the location where the light is. Pyramid, sphere, chair. So all will have. As per the need, we'll comment it out and we'll enable whatever we need. We have a transformation. So it's like a hash in the sense dictionary, or X in shapes. Okay, so whatever shapes we have, for each shape there is an array. So that is the idea. Shape equal to initial shape equal to light cube. Pyramid equal to cube equal to chair equal to none. Okay, so there is a global rotate. We can global way we can rotate the angle. So I think we can include this. There is no harm. Global rotate angle equal to 0 and light type G equal to directional. So we will have directional light first, but we can change it on the runtime, and cube scale, how big the cube will be. So we can, if required, we can minimize, maximize the cube. So that is the idea. Now the crucial part, that is the init. So this is in OpenGL, init is a crucial part. So global is pyramid chair, GL clear color 0 0 0 0, GL shade model is GL smooth. This is what we are considering. So everywhere it is GL smooth. So GL smooth shading model. So this is what we are considering. GL enable GL lighting and GL enable GL light. So there can be many light source, I believe up to 8. So we are using light source 0, that is the first one. GL enable GL depth test, and pyramid equal to pyramid, cube equal to shape, and obj equal to. So we are using the object file that we receive from Blender. So Blender is a tool which generates the object file for the shapes what we draw there. Okay, so just for showing what is the Blender we are using. So this is a Blender. Like this is the cube, and we can save it. So generally we use triangular faces. So in edit mode, we have to go and face, make sure it is a triangular face, and then we can just export, and that's it, and we get the cube. So we are using Blender. So for the obj file is cube211.obj. We'll copy this cube. We have this file, and we have a chair also. So chair is also a shape of equal to chair.obj. Now we'll have a display. GL clear, GL color, buffer width, GL depth, buffer width. So every time we do the display, we don't forget to clear the buffers. So one is the color frame buffer and another is depth frame buffer. So both we clear. GL push matrix, GL translate, so translate F. So whenever so we are translating, pushing the item at -5. I think we have showed this. So if this is the camera, if this is the projection, then in the projection, the local coordinate is 0, 0, -5. So this is what we are taking into the account. GL rotate, global rotate angle. So we have option of rotating everything along y-axis. GL rotate, global rotate angle. This is what we have taken, global rotate angle along y-axis. I think it should not be a tuple. For L shape, in shapes, GL push matrix, GL translate, if length of x greater than 3, else GL rotate x, for x in transformation of the L shape. So what we are doing is in the transformation, so we are keeping a transformation matrix for every shape. So whatever we are transforming for each shape, we are getting the transformation matrix, and in the transformation matrix, if it is length is equal to 3, means that is a GL translate, because for rotate we need 4 angle and then followed by like this. We have rotate, so angle and the 3 axis, where in translate only 3 axis. So if length is 3, then it is a GL translate, or otherwise it is GL rotate. So that is the idea. If L shape equal to light Q, now if the shape L shape okay, so if L shape equal to light Q, GL light FV GL light 0 GL position okay, so it is at 1.5 in Z direction and it is 0 if light type G equal to directional, else it is 1.0. Okay, so we have enabled light and we are setting the position for the light. So this is what we are doing. This is the position of the light. So position of the light is from the local coordinate, it is 1.5 in the Z direction. So GL light FB is GL light 0. For GL light 0, GL position is 0, 0, 1.5. 0 if light type is directional, S 1.0, that is the positional. I think it is straightforward. GL translate 0, 0, 1.5 and we'll draw GL disable, GL lighting, GL scale, cube scale G. So we will scale as per the, so we'll use floating point. So depth display, GL rotate F, translate F, rotate F, scale F, okay, so we'll proceed. Now we will draw the cube. So cube display, this is the API we are using, and color equal to 1.0, 1.0, 1.0, so it is white. Side color in the sense that what would be the color. So what we are trying to do is back side, it would be kind of yellowish. This is the back side, that is the back side of the cube. Front side should be red, like we can see that front side is appearing here, that is red. Back side is slight yellowish, so that we can identify it. So 0, 0, minus 1, so it should be red. 1, 0, 0.2, 0.2, and backs and the side near to the camera. So this is the side. So minus 1 is far away, and 1 is, that is minus z axis, 1 is z axis. So that we'd set 0, 0, 1, 1, 1, 0 point. It is kind of yellow. Okay. Now we will enable the lighting. We disabled because the cube would not be drawn nicely. Enable GL lighting. Okay. If L shape equal to pyramid dot display with the default argument, if L shape equal to sphere, GL material, GL front, GL ambient. Okay. So for the sphere, we are making sure that ambient is kind of blue. So 0, 0, 1, 1.0, GL material, GL front, GL diffuse. So diffuse we are making at green. GL material, GL front, GL specular 1.0. So specular is white, 1, 1, 1, 1.0. GL material F, GL front, GL shininess, kind of we can set 40. Glut solid is glut API sphere, and it is 0.5, 40, 32. These are latitude, longitude. If L shape equal to chair dot display ambient equal to 0. So here ambient is green. Diffuse equal to, so its color of the chair is kind of red and blue, so I think that is cyan. Specular equal to, what would be shininess? So that is white, and shininess equal to 80, we will make 40. Okay, so we'll have a GL pop matrix and GL pop matrix. So this is the display. So this much is expected in OpenGL. So material color will place it as F. Real F. Okay, so we will have GL material, so all are float. So we are making sure that everything is float. Okay, so now we'll proceed to the reshape. Reshape we get width and height. So we'll have a global transformation what we had. GL viewport 0 0 and GL matrix mode is GL projection, GL load identity, GLU. So we are taking perspective so that at least depth we can, it should be visible. So 40.0 width by height, if width is greater than equal to height, else height by width 1.0 and 10.0. We can use ortho also. So probably we can type the code in experiment we can just enable it. So GL ortho minus 1.5 minus 1.5 into width into height by width 1.5 into height by width. So 1 to 20. If width is less than equal to h, else GL ortho minus 1.5 minus 1.5 into width by height 1.5 into width by height 1 to 20. Okay, so 20 we can change with 10. Okay, so this is the code. So in reshape we have GL viewport, projection load identity, GL perspective. Now, so GL perspective actually we are specifying as the projection. Now we will have GL matrix mode, GL model view, GL load identity, transformation equal to x. So if someone resizes the window, then it would kind of reinitialize it. Now we will have a keyboard. So keyboard is important because we will have animation through it. So keyboard gives key x and y. We will have global transformation because we are changing the transformation. Shapes, shape, global rotate, angle G, light type and cube scale, key equal to bytes. Key, so we make sure that key is byte. If key equal to BT, if it is a tab, then we'll change the shape. Shape equal to shapes. Shapes dot index, we find out what is the current shape and we just increment it by 1. shapes. So we move the shape. Okay. Util c dot. So in the util, we have a util OpenGL util package. So in that package we have keyboard. So that takes care of the key, and we pass the transformation for the shape, and it modifies the transformation internally. If key equal to p, then we will change it positional and directional. So probably I think we can make like this: light type equal to direction equal to positional. If key equal to p, else directional. I think this is the better way. Okay, if key equal to positional, light type G equal to positional. L if key equal to capital P, light type G equal to directional. Okay, so to print the states, in what state it is, so we'll have a BV. So someone wants verbose. So in util we have util. We'll show the util file. We have pretty print. In pretty print we have to show what we want. So we can say like we want shape equal to be printed. That would be shape. We want transformation equal to printed. That would be transformation matrix. We want light type to be printed, and that would be light type underscore G. We want global rotate angle to be printed. That is global rotate angle G. So that's it. Now we will have light cube size to be modified also. So if shape equal to light cube and R is set. So if it is capital or small c, key dot decode, because we want a string. If this is the case, then we'll have cube scale G equal to. So we'll increment by 0.05 if key equal to capital C, else we'll have max 0 x minus 0.05 for x in cube scale G. Okay, now we'll have global rotate angle. So this much pen is required in OpenGL code. So this is, I would say, minimum. Key equal to BG, else minus 10 plus 10 if key equal to BG, else minus 10 if key equal to capital G, else 0. Glut post display. Okay, so we are done. Now I'll have all the formality. If it is a main, then what I have to do is glut init for glut functions. Then we'll have glut init display mode. Glut single we are using, glut RGB, glut depth, we'll do window initialize, window size 500, so like this. Glut init window position, that will be 100. Glut create window my light code. So we'll call init function. Glut display func is display. Reshape func is reshape. Glut keyboard func is keyboard. Then we'll have glut main loop. Okay, so we are done with writing the code. Okay, so we'll browse it once before we actually start compiling, executing it. So we have OpenGL import, glut import, RE, and we have shapes. We have a transformation, shape equal to light cube, pyramid cube chair none, global rotate angle G 0, light type is directional, cube scale is 0. So in the init we have global pyramid because we have to instantiate, clear color is 0, smooth. So we are enabling lighting, light 0, depth test, and so we have done this lighting. So if I see, then this part first I have to enable. So specular and diffuse, they are by default, diffuse and specular, by default it is 1 and ambient is 0. Okay, no one stops at making it explicit, so that we can also do. Okay, now, so pyramid we instantiated, pyramid shape, we have a file called OpenGL util, from there we are getting this, and now we have display, so we clear the buffer, push the matrix, translate the local axis, we can rotate as per required just to show the procedure. Then we have L shape in the shape, GL push matrix. If it is a light cube, then this is the grammar. Here I can push in. So we are setting the position. No one stops at making me GL light FV GL light 0, GL specular, and that would be 1.1.1.0. So I can do like this, but this is anyway it is default. So these are anyway default. Okay, so GL position we set and directional it is 0. Translate disable lighting, then we draw the cube scale G. So cube scale G is uh, the cube what we get. So we'll scale the Q, scale G as per, and finally we display the Q. We enable the lighting back. Now we have pyramid and pyramid display. If it is sphere, now we are setting the, so in the pyramid display mode, we are setting the GL material. For the sphere, we are setting here only. So two part, one is light part and one, this is the light emission and this is the light reflection. So that this will come as GL light V, GL light V, and this will come as GL material F. So that is the difference. So GL material FV in similar way. For every, so this is a kind of a state, means if, so this is for everything. I am drawing pyramid, so everywhere we need to change. Like if it coming to a sphere, then it will be, then same thing will be applied. If I don't have a color material tracking, that is another way we can track it and change it, but we are not using that. So this is the way it is. Then we draw the sphere. If it is chair, then we set ambient equal to, then diffuse equal to, then a specular equal to, and shininess equal to. Now we pop the matrix, and we flush it. In the reshape, now load identity GLU perspective. So that we have set. Model view, we have load identity. If someone reshapes, then shape is gone, all transformation matrix is gone. In the keyboard, we have light type and here shape would change. So keyboard is only one, so we can focus on a particular shape and we can transform it. So that is the idea. Keyboard handles the transformation, return the transformation matrix. Positional we can change, directional. If it is V, then we will make a pretty print. That is the idea. If it is a light cube, if shape is equal to light cube and it is a C, then light cube we would change, and then for global rotation we'll make it and glut read display. So we have glut init, display mode. So single, we are not using double. So coloring would be nice because we are not using high profile OpenGL speed. We are not taking that, so it should be okay. GL create window init display function reshape keyboard. So I think we are done. Light type. Okay, so it's okay. Okay, so we have only one file. Now, the way we showed, so we have other files also. So we'll copy called OpenGL utility here. We'll copy chair.obj here. We'll copy cube21 dot here. We'll copy obj loader here. Now we have these many files. So we'll say Python 3 GLLT. Okay, so if name equal to for x (67). Color is not defined. 42 substitute color. GL material, FV, GL front, GL diffuse. (48). Okay, we are getting. So we are getting all the steps. So I can print where what is my state. So I pressed V. Okay, so V is giving error. Local variable global rotate angle G reference before assignment. Okay. Global rotate angle okay, so I'll press V. Okay, so it prints the right now we are in the light cube and it is light cube pyramid sphere chair. Light type is directional, global rotate angle is 0. So probably I can change the pretty print little bit. Print transformation equal to light type equal to and angle G equal to. So this would be better. Okay, so I print V. Okay, so shape is light cube and transformation is for the light cube there is no transfer pyramid sphere chair directional global. So now I have this. So right now it is light cube. So if I press Ctrl C, cube should come. Shift C, cube can become bigger. Cube can become smaller. Where the cube, I can press G to see. So cube is at a distance of 1.5. So here we are. Near is 1, far is 10, local is 5, we are at 5, and from here cube is at 1.5 distance. That can be seen. So cube is a little bit a distance from these entities. So we have drawn everything, sphere and chair. So I can say tab, then I can print where I am. So I am at a sphere. So if I press tab again, tab, and then if I print, so I am the chair. So I can bring chair pressing near N. If I press N, chair would. Okay. So since we have rotated the angle, so chair is moving towards the camera. So camera is on that direction. Okay. I can bring it back. Okay, so this is what initially we are getting. I can push chair down. I can rotate chair. along x-axis also, along y-axis also. So this is the chair, and along z-axis also. Okay, so we'll move. So I'll show the code of the OpenGL utility. That is the promise. So OpenGL util. So OpenGL util has a class utilC, and it provides a function like normalize, get normal vector, display. So in the display, we set the ambience, specular, shininess, diffuse of the shape, and this is GL triangles. So the mode of the draw is GL triangle. That has to be okay. Get buffer is if I receive buffer from the obj file, where to trim to get the, you see, interleaved buffer. This is to get the color and get the vertices, the normal texture. Then it has a keyboard. So keyboard we are using, and then it has pretty print, and it has a shape. So whatever shape we want, then it initializes the obj file and vertices, normal, indices, and then it has a display shape also, which calls util.c, and pyramid we have separate init file, and vertices we have hard coded, indices, color, normal, and finally we have display for the pyramid separately. So this is the architecture of OpenGL utility file. We have obj file. Obj file we have downloaded. It's a obj loader. Otherwise, from the Kiwi resources, we use resource find, and then we have debug write print. So this is kind of modifying the print. Okay, so we'll proceed with the laboratory. So in the laboratory, first we have lab session, we have directional, then we have positional, and we don't have chair now. So what we can do now is we will open the GL light, and in the shape we will have pyramid. We don't want chair, so we'll, and we can let execute. Okay, now we have, this is a directional light. It is coming from infinite distance. Now we'll select sphere. Now mode is directional sphere. I press 2 times tab, it came to sphere. Whatever key now I press, it will go to sphere. So idea is that so we'll make sphere move, right? Now it can be seen that light is falling on the sphere. So sphere, it is going right side because of the GL perspective. If I use GL ortho, no one stops me doing that. We will now try in ortho fashion. So I'll comment this. So this is ortho projection. So this projection, so we are taking now ortho, otherwise we are using perspective projection. So now in ortho, if I take the cube right, Okay, so we can see that the shininess or a specular is at the center. We can try both. So the old one. So right side is perspective and left side is ortho. And if I take, so there is a difference. So in perspective, the directional light changes because perspective is not the uh, a typical cuboid. So that is the difference. We'll go with the perspective. Okay, and if you see the keyboard, so keyboard is like LRDUN, left, right, up, down, and XYZ is rotate along XYZ. And if we see here, if I press tab, then shapes would change. So whatever shape is in current kind of focus, so that would take the keyboard. So that is the idea. So from the OpenGL util package, we import util C shape. So util C contains the keyboard for the left, right, or something like that. And in the keyboard, P and capital is for positional and directional. The way it is, we print the current state, and light Q we can kind of make it big, small. Now we'll come to original discussion. So directional light is placed at infinite, whereas positional is 1.5. This is what the design is. So we will take out the sphere from here and we'll place somewhere here. So we can do something like this. Idea is that we'll take out the sphere from this place. First we'll place it here, then we'll take it right. So that is the idea. Take here, then to the right. Now we'll see the difference. So cone would be kind of straight in the minus z direction, and this would be in the positive x direction. So this we will get. Okay. I'll recheck what is the condition. Okay, so we'll use GL perspective and comment the GL ortho. So that is the idea. Now, what I will do, I press 2 tab. If I see the situation, I have selected a sphere, and transformation for the light cube, pyramid and a sphere is empty. There is no transformation. And now I can bring a sphere in front, and if I see the condition, it is 1.2. It is 1.4. Now it is 1.5. So 1.5 means we brought the, so cube is now here. cube is here. Now I'll get it to right side. So this is directional, means light is positioned. So if I see the code, okay. So in the code we have placed it 1.5, 0, 0, 1.5, but 1.5 for the directional light is along 1.5, 0, 0, only Z component is there, positive is there. So on the positive side, it is at infinite distance. So I can prove that first. I can say left, 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 far, 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 far. Now I can bring so this is the light cube. I mean, I can kind of rotate it. So this is the light. Now I'll take the sphere in the front, in the near. It came above the light, still it is glowing. This proves that light is not there. The light cube is drawn here at 1.5 and sphere we are bringing beyond this. So light is here. So this side should be shadow, but it's not shadow. So light is not there. In direction, light is at infinite distance. It will cross the projection matrix if I make more near. Okay, so this is what it is. So gone. So light is not there. I'll see the situation where it is. It is 2 point. So sphere is 1.34. So it is 1.2. Now I can make it right. And I would change it to positional now. So I shall press P. This is positional light. This is directional light. This is positional. In the positional light, the light is at 1.5. Light is here. So no one stops me doing the same experiment. So where I am? I am at a sphere only. So I can say left, 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 gone. There is no light. This is ambience. Blue I have set. So if I say far, okay, so light is appearing and appearing and appearing. So this is positional. Whatever we see the area where there is no light, this is the ambient light. Whatever we see the green part, this is the specular light. This is the diffuse light. And this white light is the specular. And at the center what we see the highly shining, that is the shining amount. Okay. Next thing, so if we see so directional light, it is at infinite distance. And in the pyramid, there is 5 vertices. 1 vertices, 2 vertices, 3 vertices, 4 vertices, and 1 vertices is behind the scene. So there are 5 vertices. In the 5 all vertices, whatever receives the light, that should glow. Okay. So I think I can show it later because that is not right now. So now the next is so if I see the position and direction. So direction we saw, where is the direction? So direction is omni and light in the directional is positioned at infinite distance, whereas in the positional it is at nearby. Okay, and we can see that it's only blue, whereas this should be. Now if I move the light up, this is positional light. Now red vertex is getting the illumination. So vertex, whatever is getting the illumination, color of the shape would be like that. It doesn't matter what is in between, pixels or fragments or its area or surfaces, only vertex. If vertex receive light, then only blue is receiving. Other became. So this is the concept. So let's move. Now we have transformation. So light can be transformed. Light can also move. Like I can move the light. It's clear? Light is on back side. So pyramid has no light, and this one is ambience is blue. So this is what it is coming. Okay. So light can be transformed. I can show on the chair also. So I have another example with the chair. I have a chair, and if I see the constituency of the chair, okay, so if I see the chair display, so chair is ambience is blue, red, green. Ambience is green. Diffuse is cyan, and specular is white. So if there is no light, it should look green. Otherwise, diffuse is cyan and specular is white. Shininess is 40. So this is how it should be. So diffuse is white. As we can see, I can bring the Q, and this is positional light. This is directional light. So positional light, this is the front part. So diffuse is coming into the picture. Otherwise, this is the actual color. Okay, I can rotate the Q along x-axis. Okay, so light is not reaching this part. So this is the ambience. Light is reaching nicely here. So this is white. Otherwise, this is the color. Okay, so this is positional light. So I'll keep on. Okay. Now, as light is more focused, the specular part is more prominent. Now it is completely white. Okay. I can rotate the light. I'm sorry. Okay, when there is no light, it is green. This is the ambience. Okay, this is the actual color. But if light come near more, then this is the specular and shininess. So what I want to show is that light has transformation, object has transformation, object has transformation. Light has transformation. Light can go up, it can go down. I mean, there should be a difference, I believe. Okay. Light can go right. Okay, difference is coming, but it's not highly visible. Probably we can, okay, difference is there. Okay, so right can move up, down, left, right. Light can rotate. Okay, so transformation is possible in light as good as it is in any model. Okay, now we have color emission and reflection. Okay, so whatever color we have for the light, if that color is not doesn't belong to, so I think, okay, if light is only red, reflection is only green, then as per this model, this will be 0, this will be 0, and this will be 0. So there should be only ambience. Now I am going to, okay, so we'll bring back sphere and we'll see. So we'll change the light as per the design. Okay, so light diffuse is only red. So the light coming from the source is only red. Sorry. And the sphere color, you see the sphere color, the diffuse is only green. Red is emission and reflectance is green. So it should not do the magic. So I am going to show it now. So we'll make it a sphere. We'll try now. Okay, so there is no light. This is directional and this is positional. Still only ambience is there. Now I can rotate it. Okay, I am not, I think I am pressing R. So I'll press Y to rotate along Y axis. Okay, I think I should show the cube. This is the light. So no green. I can change the color of the light. Now instead of red light, it has green component also. Red component is there, green component is there. Let's try. Wow, this is what we wanted. Now it's there. Now I am free to, I can show the cube. I can rotate now. So this is the light model. Okay, we'll try if really it becomes complete black. So we'll make it again 0 as green, and in the ambience we will make it 0. So there is no ambience, it is black. It is really black. Okay, so if there is no ambience, so I can show the cube, and if there is no ambience, so a specular is there because I have set a specular as white. Otherwise, there is nothing. So white shininess is coming because there is a specular one, and here in the sphere there is a specular one. Okay, so I'm not going to change it. So we'll keep it as, and here, so light also will make it 1. Okay, so this is the idea. Now we'll proceed to next example. Light intensity. So color is dependent upon the light intensity also. So intensity of the light. So how much intensity? So if light is 1, then it is pure green. If it is half, then depend. I can change here, I can change there, anywhere, because after, at the end, multiplication happens. Okay, so I'll change at material first. So in the material, diffuse is 1 point. Okay, so this is full, and for the solid sphere, diffuse is 0.5. We'll try. Oh, so if color intensity is different, then also color changes. I can try through light, or I think it should be okay. It will work in that fashion only. Okay, now if there is a light that is at the not at the vertex, then will it be black? Here, so if we need very nice color, then we have to go for tessellation, and there should be many triangles. We are using triangles, so we have only 4 vertices. Okay, I can show the cube. We'll go with pyramid. So I'm checking if we have reverted back. Okay, it wouldn't matter for pyramid though. It's okay. So this is our pyramid. I want to glow it even nicely. No one stops me. Making it diffuse as 2. Okay, more shining. Now we'll have positional light. Okay, let make it directional so that at least it should be. Or positional, then we have to go far. So if I say near, the light will come near, and more nice the I can remove the light. So this is positional light. Now I can just rotate it and I can show. This is a pyramid. This is a pyramid. This is a pyramid. Okay, so we'll come to the. Okay, so if I resize, then everything comes to normal because this is the code. If I resize, after low identity, all transformation matrix are reset. Now, this is the. Okay, so okay, I think positional. Okay, so we are at pyramid. Okay, now this would work. Okay, now this is the light source. I can rotate the light source. I can move up. Looks nice. Let's move near to the pyramid. Gone. So light is directly falling. It is so near to the pyramid that vertices are not receiving the light at all. So light is in front of the pyramid, but it is nothing. So this is OpenGL. If I move up, then red vertex is getting the light and little bit green and blue. If I move down, sorry, okay, if I move down, nothing. So this is OpenGL. I can bring near. So light is coming near to us. If I press far, light is going towards pyramid. There is. So light is going away. Okay, so we showed all the experiments. In a smooth shade model, light must fall on the vertices. Light intensity changes. We can change the light intensity. Color emission is color based. The color component in the light must have the color what material want to reflect. Transformation happens in light also. Transformation happens in directional light also and positional light also. Both. So, if I bring at the beginning it's directional. This is directional light. So, if I rotate, so just for showing but this is not exact position of the light, but still if I rotate, directional light also rotates. To prove it better, I can bring in another guy called chair. So this is directional light. Okay, this is positional light, this is directional light. So just for simplicity, now if I rotate, directional light also rotates. Even though it is at infinite distance. This is positional light, this is directional light. Okay, now the directional light is at minus z axis. Sorry, it is at z axis at infinite distance. We can see that chair is completely illuminated. If I bring the chair near to us also, then chair would be visible. If I make it P, positional, okay, so ambience what we can see mainly. Okay, so we covered directional and positional light, position and direction. So whatever position we set, that position is actually positional light, and for the directional, this position axis it takes. Transformation we showed that light can also move. Color emission, light of the color and light of the material matters. Light intensity, we can change the intensity of light through material and through light both. And it's a smooth shading mode. In a smooth shading model, vertices should be illuminated. So we can make it kind of tessellation, and we can make it many triangles. So there will be many vertices, and it would be illuminated in better way. Okay, so we'll move towards next exercise. That is light model emission and ambience. So that will be emission of the material that we will see now. Light model emission and ambience. So we'll see the light model emission. So if we see, there are three things. One is light source. It can be many in number. Only one light model. And from the light source, ambient, diffuse and specular, three component of the light comes into the picture, whereas light model add ambient. So each light source has three, where there is only one light model has ambient, and then material has these many reflection properties. So this is emission and this is reflection. Now once we see the calculation, the light received by a vertex is emission of the material, ambience of the light and ambience of the material, and then per light model. If light model is n, per light model, this is called attenuation factor, spotlight effect, and then ambience into the light and that light I, and material and diffuse of the material, and shininess of the material and the light. Specular shininess of the material and the light. So these factor adds up and make the lighting at the vertex. So now we'll see the ambience factor. So ambience of the light model, ambience of the material, and then ambience of the material and ambience of the light source. Okay, so light model has a parameter called GL light model ambient. So we'll open this file and we'll add a GL light model. Okay, so there is no GL light model. So where we should add in the init, here we'll add GL light model FV GL light model ambient. Okay, so there are many scenarios. That's what we are seeing. So this is the a kind of a normal scenario. Okay, so we'll make it as a kind of 0 point. Okay, so that is the lab session. So lab session first it should come as yellow and red, and then it should come as green. Okay, so we'll make it as like this. So this is the light model ambience. And here we will add GL light, FB GL light 0, GL ambient, zero, 0.2, 0, 1.0. So what we are doing is, here it is green and here it is red. These are the two ambience we are adding, and we'll have here pyramid and cone. So we'll add one more guy, that is cone. So light cube, pyramid and cone, and we'll have ambience like this. So light model. So I want to show that there are two ambience. One is red and one is green. As per the calculation, this ambience should also take into effect, this ambience should also. So if this is light and if this is green, so as per the formula what we had, LR into MR, LG into MG, LM, LB into MB. So with this formula, okay, this should add red component, this should add green component, and if this ambience is white, it should look yellow. That is the idea. Now we have shape equal to sphere. Now we'll have 2, 3, 4, 5, 6 YY, and we'll have shape equal to cone. Okay, front ambience is 1. Okay, so 0.5, this is what is the experiment. 0.5, 0.5, 0.5. Okay, and then diffuse is, okay, so diffuse its color is green, sphere, so it's okay. Specular is 1, shininess 40, and this is what it is. Now for the cone, it is 0.5. So this is the experiment we are doing. 0.5, 1.0, and this would be red. So cone should look red, or here it is purple, so we'll make it purple. Diffuse, specular is 1, shininess. So here we have blood, solid cone, where this I can make 0.8, 40, 32. That's it. Now we have three ambience. One is material ambience, and then we have light model ambience, and this much light we won't throw now. And then we have new called light model ambience. Now we'll practice. Okay, I think pyramid has come. This is what we don't want. sphere. Okay, so I have now, so I can make a sphere move, right? Now I have a sphere and I have cone. So I can show the cone. There is no hesitation in there. So this is the cone. Now we can see the diffuse, that is green, diffuse is purple, and then we can see the specular and shininess, it is visible. Okay. Now we'll see the ambient is not visible here. So what we can do, so we'll show the light. So this is the light. So we'll rotate the light. Now both are yellow. Okay. So yellow would be more prominent if we increase the ambience. Okay, so we'll increase the ambience. So here 0.02, instead of that I can make 1.0 or maybe 0.4, and here also 0.4. So it would look little brighter. Okay, I think this is, we press twice, so that's fine. Now we will rotate. Now we have light source. Yellow is prominent now. So this is the ambience. So ambience is yellow. Ambience is yellow because both ambience are coming into the picture. If I comment this, no ambience from the light model. So if I comment, there will be default ambience from the light model. So I would deliberately make it 0. No ambience from the light model. Only ambience from the light source, that is red. So now ambience should be red as per the formula. Okay. So lighting has come. Now we can go. Okay, so it okay, so we can rotate now. Okay, so ambience is green. This is what we are seeing. We expected red. So let's see. So clearly it is green. Oh, it is green. Here it was red. So here it was red and here it is green. So we can make it, so ambience is green. No, it's not yellow. If I set it here 0.04, then it would come as yellow. Red and green and multiplied. So now it would be yellow. Okay, so it is yellow. If I want to make it red, leave it as red and this light source will comment. So instead of commenting it, we will make it 0, forcing it to nothing. So now it would be red. Okay, so ambience is clearly red. So this is the light model, and so we covered this in lab session. We covered the this. Now, what about the ambience of light model and ambience of light source? Both as 1. So, these would emit ambience 1, and this guy will have different kind of reflection. So, we are proving both the things. So, what we can do now is, now this we can make as white light, white dim light in ambience, and here also white dim light, and in the sphere ambience, the sphere will make red, ambience as red, and cone will make it as yellow, as green. Okay. Sphere is blue, and this is green. So sphere is blue, so this is blue. So sphere is blue and it is green, and both light source, this light source ambience is white and this is white. Now we can try again. Okay, so I have light source visible. I can rotate. It is quite clear that one is blue and one is green. We can make it more prominent. One also, if I increase, it should be okay. We can see that this color has also changed because ambience also comes into the picture. Okay, so it is more prominent now. One is blue and one is green. So this is the idea of ambience. So ambience has two sources. Only ambience, not others. So light source also emit ambience, and light model also emit ambience, and these two ambient finally get multiplied to the material ambience, and this is what it reflects. So we don't want this big ambience, so we'll close this. We'll reduce it because accidentally it will be very big. Or we can altogether comment this, because anyway it adds the default ambience. This is the default 0.02, and we'll comment this also. So this is our ambience. Now in next lab, okay, we'll see a model local viewer. So we'll cover this part anyway. Emission and ambience of light. So this is what we have seen. Ambience of light model, ambience of material per light model. Sorry, per light source. Ambience of light into ambience of material. Now, if I see ambience of color model like this, light model, light source is different, that emits the diffusive and specular, whereas light model adds ambience, but light model adds more things also. So we can set light in light model, we can set ambience. This is what we did. In light model, we can set local viewer. What is local viewer? Right now we are talking about camera is placed at 0, 0, 0. It's not. In the reality, the camera is placed at infinite distance. Okay, we are showing camera is placed here, but in reality camera is placed at infinite distance in z direction, z1 direction. Okay, it is not here. Okay, so it is somewhere in the infinite, like the light direction is at infinite, it is also at infinite. How it make difference? It doesn't make any difference. It is here or here, but in specular calculation, so there are three part: ambience part, no difference; specular part, diffuse part, no difference; ambience part, no difference; diffuse part, no difference. But in a specular part, there is a difference. So now if I see this calculation, a specular of the light, okay, now if I have a light source, I think we have this, right? Okay. We have not had it. Okay, so we'll draw it. Now, if I have a okay, so if I have a light source, and this is the surface, so this is the surface, and this is the light source. Okay, so this is the light source, this is the surface. Now, few things that comes into the picture is normal. If this is the vertex we are talking, normal of the vertex, that is in this direction. Light falls on this direction, and light gets reflected in this direction. Where is our eye? Eye can be somewhere here. Okay, so this is our eye, and this is the reflection, and this is the normal, and this is the light. So eye, if eye is in, so there are two directions. One direction is the light direction. Okay, so one direction is the light direction and other direction is the normal. So both should be in parallel to have the better effect whatsoever. And reflection direction, so eye should be in reflection direction to see the shininess better. So this is only for a specular. We are talking only for a specular. Okay, not for the ambience or diffuse. For a specular, the shininess, the light direction and normal, one calculation, and vertex normal and the eye in another calculation. So these calculation matter for the specular. So now when camera is here, suppose the light model is this model is here, and light is coming from the infinite direction from here. If camera is at infinite direction, the shining should be here, shining should be here. If camera is not at the infinite direction, it is at 0, 0, 0, what we had earlier. Then if light is coming from infinite direction, then shininess, now light is coming from, but this is the camera. So, okay, so shininess would go down. It won't be at that location. So it matters. The idea is it matters. Camera is near or camera is far. It matters. So this is what we are trying to see. Okay. Now we'll see in the chair. Like chair, this is when camera is at infinite and camera is at 0, 0, how it matters. We'll see in the sphere also. I think we can see. So what we would do is, now in the code, we'll change this. So we have perspective right now. So we'll make it ortho. Okay. And we'll have only sphere. And we'll see the difference. So we have a sphere only, and now we'll see how much it is different. So ambient is 0.5, it is very high. So we'll just make it 1. Okay, and it is, now we'll plot the, okay, we'll move it up. This is the default, means camera is at infinite distance in the Z direction. So I can close this and I can open like this. So we can modify the code. Now okay, it should go up. Nothing. Okay, so I think caps was on. So I can try again, and now we'll modify the code. Now, as per the, now we will have a local viewer. The camera is local now. So we'll add GL light model. Now it is a local viewer, and local viewer is 1. So camera is now at 0, 0. GL light local viewer 1. So camera is now here at the 0, 0. Okay. We'll see if it really matters. So camera is now, the default is 0. What we are seeing, the output, it is 0. Now we'll make it 1. We'll try again. GL light local viewer is not defined. Okay. So we'll see what it is. GL light model local viewer. Okay, so we'll move it up. Is it different? That is the idea. This is local, and this is camera, it's placed at infinite. So both are, certainly both are different. We can see the spot is down. Here spot is at center. Spot is at center because camera is at infinite distance in Z direction. Camera is near now. So spot is coming down. It will be more prominent if I move up. So it is going down even. It is going up. If it is, we can see here, it is always be at center. Okay, so certainly that is up. So this is the change. We can bring chair. So we have chair, I believe. Okay, so chair ambience is 1. Okay, so it is too big. And diffuse purple, the specular is 1. And so ambience will make little less, kind of 0.5. And diffuse is purple. So we'll display chair. Instead of sphere, we want chair. Let's see. Okay, Mr. Chair has come. And this is the local one. So we can move up. We'll keep it right. Now, we'll comment this, the default one. Okay. This is the infinite one. Is there any? Okay, we'll move it up. Is there any difference? There is difference. So if camera is infinite distance far, then we can see the specular component. Here we can see the diffuse component. Since camera is down, it sees from the down. So upper part of the chair, the color is coming. If camera is at infinite distance far, it would it is in the direction of the light. So it generates the specular component. Here it is not able to generate the specular component, and diffuse component is taking the prominence. That is clearly visible. So this is where camera is near. And this is where camera is at infinite. So these are the fundamentals only for specular, not for the ambient and diffuse. So this we have to take care in the calculations. So we saw this in lab, local viewer. So we covered this part. Diffuse light direction and in a specular light direction, this is the normal, and then S is this. So here S is this guy dot this guy one side, and this guy normal, and I dot this side. Then we add it and we get the S. So in other calculation, only the light direction and normal comes into the picture. Here normal and I direction also comes into the picture. So this is specular. So we have covered this ambience part and specular part. So this is what a specular is. So how shininess differs, we'll see more into a specular if time permits. So we'll come back to original. Okay. We may not comment it. We'll make it 0. Both are same. If I make it 0 also, it is same. Okay. Okay. So local viewer we are making as 0. So this is okay. So we'll see. Okay. So both are different. So if I make local viewer as 0 instead of commenting it, so if it is at far distance, so I think it's right. If it is far distance, then we can see if it is far distance, then we can see the specular, and if it is at near, then there is no specular. Diffuse part is prominent. Okay, so we'll move. So we'll comment this because experiment is done, and GL ortho will bring it back now. To perspective. Okay, so in next exercise, we'll see another property of light model is called model two side. Okay, I'll bring a coffee mug. Okay, so I don't know how big it is. So I have coffee mug. So I have one dot ob coffee mug dot ob. I'll copy it here, and here we'll have, instead of chair, we'll have coffee mug, and we'll have one more guy called coffee mug, and here we'll have coffee mug, and here coffee mug dot op. Now here we'll say if it is chair, very nice. If shape is coffee mug, now we'll show coffee mug, and same thing, diffuse is purple, specular, and shininess. Okay, so let's try. Okay, so coffee mug is quite big. I think we can make it smaller. So we'll put a scale, GL scale, F, kind of 0.4. Now we'll see. Okay, so it is I believe too much shininess. So what we can do is we'll decrease the shininess, and we'll increase the size also. I think it is too small. So 0.4 to kind of 0.8, and shininess we can do. So specular will make less, kind of 0.2 should be enough. Okay, so we have coffee mug. Or we can just remove the specular will make it 0. It is shining too much. Okay, so this is coffee mug. Now coffee mug is hollow. If I press X, okay, So the greenish part is the ambience part, but we can see the surface of the cup has same color. This part and inside part, inside of the cup and outside of the cup has same color. Okay, this is what we don't want. We want a kind of a cylinder. This is a cylinder. We want a cylindrical shape where outside color would be different and inside color would be different. Here outside and inside both are same. So we don't want this. We want different. So the calculation would be that the outside of the cup. Okay. So outside so when we go for the coloring kind of it bounces on the normal. We have to have a normal. When light falls on the normal, when light falls on the vector on a vertex, then it sees the normal. So in this, normals are provided for the outside also, for the inside also. So inside, if I remove the normal, we don't produce the normal at all, then it would come as ambience. Okay, even though light is falling inside, light is falling outside, both side light is falling. But if I don't put the normal inside, only normal calculation only for outside, then inside would be ambience. Then we can go for light model, some kind of attribute enabling, and where normal is not there, it would generate its own normal, and then we'll have different color. So that is the idea. Okay, so like the idea is we'll go for two side. Now two side means like this is a glass. Outside we can see different color and inside we can see different color. Like typically if there is no normal, then inside is ambience. Okay. So if there is no normal and if I set light model two side, then wherever there is no normal, normal calculation is absent, there we can specify a color. So that is the idea of this light model two side. Okay, so I have a cylinder. So we'll copy OpenGL cylinder here. Now in our code, so we'll kind of import the cylinder. So we'll say just import OpenGL cylinder. Import OpenGL cylinder. Now instead of coffee mug, we'll have cylinder. So cylinder we want to show now. And I think coffee mug story is over. So we can just remove this coffee mug. And here instead of coffee mug, we'll have cylinder. We'll just say cylinder dot cylinder. So OpenGL cylinder is a module. Inside that cylinder is a function. We'll just call and say, okay, just do your magic, and then we'll see what's happening behind the scene. Okay, so we can see something. Okay, something is coming. Okay, we'll try again. Okay, we see black. Now I'll show the light. It is caps. Okay, light is there, light has come, and I'll rotate it. It looks like a glass, we can see. Okay, and ambience, it looks like a sorry. Okay, I'll reinitialize it. Okay, so this is our light source. Press tab. Okay, it looks like a glass. Now, this is okay, nothing can be seen. Okay, so light gone up, I'll bring it down. Okay, I can rotate the light. Okay, so whatever light we are seeing, that is the bottom one. Okay, otherwise there is no, even though light is available, there is no light. Okay, whatever light we are seeing there. So this is a kind of two surface. There is a one front surface and there is no light. So there is front surface and there is inside surface. Whatever we are seeing, that is the ambience color. So I can change the ambience to see it nicely. So like in light model, okay, or I can add ambience. So light model, okay, wait. So we'll add a few property now, like 2, 3, 4. Okay. So front ambience, so we'll make it a kind of blue. So ambience is blue and diffuse component. So front diffuse is purple, a specular is 1, it's okay. Shininess is there. So this is what it is. So we'll show it again. Okay, so this is ambience. This is what I was saying. Now outside is purple, but inside there is no color because ambience we have set it blue. It's ambience, it's not no color. There is no color. Whatever color we are seeing, that is the outside. Okay. What about coloring inside? So if I change this ambience, that color would change. That is only, so I can make ambience black also. It is up to me. So there won't be any color at all. This is the ambience. There is absolutely nothing. Okay. What about getting the inside color? Like in the coffee mug we saw, inside color was also same as outside color. But here inside there is no vertex. Sorry, there is no normal. So since there is no normal, it will go to ambience part. So in OpenGL we can set something like this. GL light model local wear, light model two side, light model two side, and two side is 1. Now wherever there is no normal, OpenGL would calculate its own normal, that it would be the reverse of the whatever normal we are providing, and it would come as back. So we can set back color. So in the back color we'll set diffuse and specular. So we'll say back color kind of yellow and specular will set 0. Now we have so a specular is 1. So we'll copy this line and for the back it is 0. Okay, so diffuse is yellow, back, GL back, and specular is nothing, no shining. Okay, now front. Now we'll bring it back. Is there any magic? Okay. Okay. Inside should be yellow, but it's not yellow, it is white. Okay, so we are happily changing the cone. So we have to change cylinder. So it will come here. Okay. Sorry. Okay, so idea is that we should have changed. So back will get back here and back here. Okay, so we have to change the cylinder. We modified the cone attribute. So in cylinder, now back diffuse is yellow and back specular is nothing. So diffuse front is purple. Okay. Okay, we have set ambience as black, so it doesn't matter. No. Oh, what a glass it is. It is really, really nice. So, this is Mr. OpenGL. I can show the light. Okay, so light source is here. Okay, I can rotate the light. Light is very near. I think we can move the light near little far. So light is coming towards camera. Okay, so it is really nice. Now it is better. Okay, and we can see, we can rotate the glass. So this is how it is. Okay. So now in the absence of normal, we can see that we have set the, if I see the program, if I see the ambience is black. Now even if I make ambience kind of blue, it won't be blue. It is yellow only if I run again. So this is because we have done magic in the, we have set the variable called model 2 side. If it is model 2 side is set 1, wherever there is no normal calculation, there we can set back diffuse, back specular, and that would come into the picture. Okay, so this is the calculation. Okay, for this ambience. Okay, so specular is black, so we can see the black specular where it should actually shine, and here it outside specular is white. Okay, specular is white, shininess. Inside the specular is black. Now we'll change it. Now the global ambience is RGB, is blue. So I am going to comment this and we'll run another one. Okay. So this is without two side, and this is something that we don't like because we cannot set shininess or whatsoever. Okay. And this is what we want. Okay. So this is about the light model two side. Okay, now we will focus on the material emission. So material emission. Okay, so the material emission. A material should emit a light, like we have light source, and light source is always bright. This is what we are saying. The light source is always bright. Okay, so light source is always bright. What about light source changing the color of a material? It doesn't depend upon the light source. It means it should behave as a light source. It should look like a light source. Like it doesn't look like a light source. If I decrease the light also, it will get illuminated in same intensity. What about illuminating the light source? Like this cube is just placed there. Cube doesn't change its light. What about changing of a material, its emission? So we'll try to kind of emulate a situation like light source color would change. If light source color is dim, then it should throw less light, and light source color is bright, it should show more light. Okay, so emission property is the color of the material, irrespective of the light color, it should have its own color. That color should propagate. It should behave like a light source. Okay, it cannot be that bright, and it cannot emit light, but it should glow, and it should glow less, it should glow more. So this would kind of bring a model of any street light or any lamp or any bulb, so or star or sun or moon, so that we can kind of simulate with this light emission. So that we'll see. Okay, so for the now we'll bring back our code to some previous situation. Okay, so we'll have two light model two side for time being, and then we have not made much change, so things should remain the way it is. Okay, so for the emission property, so what we need to change, that we'll see. So we'll bring okay, so now if we see our program, then we have a kind of when we draw the cube, we disable the lighting. We won't disable the lighting. We re-enable the lighting. We won't re-enable the lighting. Okay. And cube display, so this color fundamental will go away, and now we'll have ambient equal to 0 and emission equal to emission scale. So now it would be guided by some external parameter. Diffuse equal to 0 okay. So means we can see that there is no diffuse at all. if there is no diffuse, if there is no diffuse, means we are not dependent upon the light source. Specular is also 0. Okay. So there is no meaning of shininess now. So this is a kind of a dumb cube. The cube doesn't receive light at all. Specular 0, diffuse 0, gone. Now it has its own shininess, and that shininess will kind of we will control through another property called emission scale G. Ambience also we are setting 0. So everything is 0. Okay, now we have one parameter here, cube scale. Now we will have another one called emission scale G equal to 0. And in the keyboard function will another key. Okay, so like here 2yy. So if it is a light cube and if we have S, so we are adding one parameter called S, and S would increase or decrease. So capital S. So here we will say emission scale, okay, will increase by 1 or by 2, and here we decrease by 2, emission scale. So emission scale will increase by 0.2 if it is S, otherwise will decrease by 0.2. So that is the idea. Okay, now so here we have to add one more guy because we are changing it. Emission scale. Now in the cylinder, the cylinder diffuse. So cylinder front diffuse is 1. Instead of 1, we'll say it is emission scale underscore 0, 0. This is emission, this is always 0. This is emission scale 0, 1. Okay, so this is how diffuse is. So back diffuse is yellow. So we'll also change emission scale 0, 0, emission scale 1. Okay, specular is so shininess we are keeping as it is, or we can also change it. Emission scale 0, 0, emission scale 1, emission scale 2. Okay, so I think we are done with the modification. Now we'll see what it is. So we'll close this and we'll execute it. Okay, now it is dark. It can be seen it is dark, and if I bring light, it is black. I can make it bigger. It is black. Okay, now if I press capital S, light should grow. It is growing. Okay, light should grow for the light source also. That is not happening the way we are thinking. Okay, so in the light source, GL scale. Okay, so emission equal to emission scale. I think there is no emission here in the OpenGL utility. So when we draw in OpenGL utility, we have not set emission. So we can change it here, or we can add there. So probably I can change it here. So GL, or we can add it there. It is same thing. So we'll add it here. Okay. So we won't set emission property here because there is nothing to take care in the library. It's missing. So we can say GL material FV, GL front, GL emission, and that would be emission scale. Okay. So now we'll try again. Okay, so we have now I can see the light that is black. Now if I increase the light emission, now I can rotate it and I can, so this is the glass. Now if I increase the light, we can see the light source. I mean the cube. The way cube light is growing, this light is growing. Okay, specular is too high. Okay, so I think the emission property is too high. So we can change this here again. Okay, so emission property is getting set everywhere. So we don't want emission here in the cylinder. So we'll set the emission 0. Okay, so lighting model is kind of it requires practice. It's not that straightforward. So I'll set emission as 0. I don't want emission property in cylinder. So deliberately we are setting at 0. Now we can try again. So I'll show the light and it is bigger. Right side will shift it and will increase the light. So I'll move this. Okay, there is nothing. So as light is glowing, there light is coming. If I decrease the light, so it looks like this is real light source. You see the cube. Okay, so I'll bring it to default location. Okay. Now I'll bring it cube near. So it will be, and we'll transfer it. Just see the now the light falling at this glass is exactly same as what it is at cube. So if cube light is decreasing, it is really behaving like a light source. Okay. It is really behaving like a light source. Yeah, I can decrease the light. Now only ambience is there. I can increase the light. Ambience of outside is blue and inside it is coming as black. Okay. So Okay, I can decrease. No lighting, there is no light. Increase. Okay, so this is emission property. So we talked here, I have a tree also that also glows like this. So that we can see, but this is what we saw now. So vertex calculation, emission of the material, that matters. Ambience we saw, diffuse and specular more we'll see. Okay, now we'll see spotlight effect. Okay, so I have a tree. So what we can do is, I'll bring it back, this emission. Okay, okay, two side is there. Okay, now I think or we can just leave it, and I have a tree. So instead of cylinder, I can show a tree, and tree will be like this. Tree dot obj. Okay, and we'll have now. Okay, so we can close this chapter of lighting, or I can show once in on tree also this lighting. I think two side is not required in the lighting of the tree, and here it will be like this only, and here instead of a sphere, cylinder, or I can say it is a tree. I mean, I am not going to, or I can just copy paste, it is up to me. So like if L shape equal to tree. Okay, what we want in the tree. So in the tree, so what property we want in the tree? Okay, so we'll copy paste this code 3, 4, 5, 6, 7, 8, 9. Okay, I think tree will come under shape, so this we can copy. Chair dot display, now it will be tree dot display. Okay, so ambience of the tree will make it blue, kind of 0.5, it is blue. Diffuse component is green because a tree will keep a specular as green. Okay, diffuse component is green, RG1. Okay, and okay, tree doesn't shine, so there is no meaning of shininess. So specular is green, diffuse is green, and ambience is 0.5, that is blue, and this is the tree. I think we have not touched Mr. Cylinder. Okay, and this is the exactly, now we can have a tree now. This is tree, and tree we have initialized with tree dot obj. We'll copy tree, there is a tree dot obj here. We'll try again. Okay, I think tree is big. We can make it small. So I can place GL scale. So I'll say GL scale kind of 0.4. Okay, so it is float. Oh, our tree is ready. Okay, and it is green. And idea is that if I bring the okay, and if I increase the light, okay, and it become white, so we don't want that. So we'll set GL emission as 0 here also. So we don't want emission here. So GL emission is 0, and we have enabled both side. So back side also it would do the magic. So that we don't want. Okay, so it is disabled. Okay, nice. Now we'll try again. Okay, now I can increase the light. Okay, tree light is green. It is not changing, but we want from, so we'll add heat here. Now in the tree, okay, so tree ambience is blue, that we are not able to see. Now diffuse, we'll say emission scale G1, and here also emission scale underscore G1 probably will multiply by 0.5. We'll try again. Oh, so this is a blue tree, and tree is blue because it is only ambience. Now we have the light source that is black. You cannot see. I shall increase the light. Okay. Okay, so it's pretty clear now. So I can decrease the light, I can move it up, the light source. Calculation is big because it is a big object file, and I can decrease the light. Lights, both only ambience is there. I can increase the light. Okay, so I think comprehensively we have a finished emission material. So we have finished light emission and ambience, diffuse and specular. So this will show now. Okay, so this is what we have finished. If emission of the light source we can set depend upon our keyboard, and if it increases, the light at the tree is increasing. Now we'll have a kind of a diffuse and a specular. So I think we have covered many times diffuse and specular. Then we'll go for great cutoff. So diffuse and specular will bring a sphere again. Okay, and okay, we'll end up this drama of lighting emission. So lighting source will bring back our original code. and this is we don't want now. Okay, so light will appear at its best, or we'll leave it as it is. I think we need to change lot of code. So we have to press the lighting. Okay, we leave it as it is, or we have to, okay, in the cutoff I don't think we need to change it. Okay, so we'll remove. So we have to remove really good amount of code, I think, where and cube scale, and here we'll remove this area. Okay, this. So now we don't want this. Okay, and here in the keyboard we'll remove this line emission completely. Okay, so source code is changed now, and now we'll focus emission scale. Okay, so cylinder emission scale. So cylinder is 1. Wherever emission scale is there, will replace by 1. Okay. Okay, so Mr. Animation is gone. Now we are at the old code, and we'll bring the here instead of tree, we'll bring a sphere. So sphere, we are trying to show. So we'll see what is a sphere right now, because we have changed the source code so many times here and there. Okay, so sphere looks nice. Okay, so we'll set the diffuse specular as 0, and we'll see how a sphere looks. Okay, so this is the sphere. This sphere has diffuse property, but it doesn't have specular property. So this is the actual color, like this. The sphere has no shininess. I mean, so this is the called okay. It has no shininess. We can increase lighting or something like that, whatever we want. Okay, so this is diffuse is there is no shininess. So for shininess we need to have a specular component. Now it will bring the shininess. Okay. Okay, so shininess has come. So this is about diffuse. So this is in our lab session, that diffuse and specular. And in the specular we have shininess. We can increase the shininess, we can decrease the shininess. So now shininess we are seeing what it is. So we can increase the shininess. So shininess is 40. If I increase shininess 80, it would shine more. Okay. I mean, I can really see what it is. So this is 80. And this is 4. Oh, sorry. This is 80. We can keep 10. I think then it would be more prominent. So difference between 10 and 80. of the shininess. No one stops us to move the camera. So shininess also moves. Here also we can move the lighting. Okay, so shininess is part of a specular. So in the calculation of the vertex, shininess comes into the picture. Shininess comes into the picture, and that is the S. So that is in the specular we have to think about the camera location also. So I think comprehensively we have covered this. Camera location and the specular. Now we have seen specular and diffuse part. Okay. Now we'll see attenuation and spotlight. So light, if I place the light away from the material, then light should be dim. That is the idea. Okay. So we'll have another component now here, that is called attenuation. So we'll set attenuation. I think we can switch it off. Okay, so we'll have another guy called attenuation, GL light model. Okay, so I think this is not we want. So we'll set kind of GL light F, GL light 0 and GL linear attenuation as 1. So for the light source 0, GL linear attenuation we are setting to 1. So in this formula, this is the constant one, this is linear, and this is the quadratic. So linear one also, if it is 1 and it is anyway 1, so it will decrease half if I move the light. So we'll see if it really happens, attenuation. So light should decrease, the idea is. Okay, now this is our light source as white. So we will bring near to the camera and we will see a sphere. Okay, I can make the sphere big. Solid cone radius 0.5, I can make it 1.0. Okay, I change something else. Okay, so solid cone I change 0.5. I have to change this. So I'll make it 1.0. And I'll see if really light has effect. Okay, I can see the light that is appearing. Now I'll bring it near. If light is decreasing, okay, I cannot see the light at all. So what I can do now is, and I can see the light, I'll move it in this direction. And then I'll move it near to the camera. Nothing is moving. Okay, this is the appearing. Okay. Now I'll move near to the camera. Idea is light should decrease. Okay, so it is not decreasing. Okay, so what is the problem? So idea is that our light source is directional light source. This is what we are using. So we'll make it positional. So in the code, if I press P, so if I see the code in the keyboard, if I press P, then I change from positional to directional. So for the directional, there is no change because light source is anyway, it is at infinite distance. So I can move it like this. I'll change it to positional. This is positional. And if I move near to the camera, it should be dim. It is really becoming dim. If I bring near to the material, it is brighter. Okay. I can change the solid to look more prominent to bring back its original size. Okay. And then the attenuation, I'll make it kind of 2. Now we have the, okay, now we'll bring it to positional. This is positional and it is really changing. I can bring, it is better. And if I bring far near to the camera, okay, so this is attenuation. If light is near, if light is directional, no change. If I bring it near to the, no change. But if light is positional, certainly there is a change. Okay, so it is more prominent. So this is how it is. So attenuation makes effect. I can try in tree model. So instead of a sphere, probably it would be better. Tree model, and in tree model, I'll keep attenuation 1 only. And in tree model, let me see the properties. Okay, and diffuse. Okay, nice. So let's try. What is there in time? Okay, so tree is appearing, and this is our, okay, light source, and this is positional. Now I'll near, I think light is decreasing, it is prominent. Now if I bring the light near to the tree, light should increase. Okay, it is increasing. Okay, if I bring near to the camera, since we have rotated the axis, it is going somewhere. So it is decreasing clearly. Okay, this is directional light. This is positional. Now if I bring near to the tree, it should glow more. Okay, so change is there. So this is the attenuation. Okay. Okay, so now V angle, so attenuation comes into spotlight. So spotlight, so exponent and attenuation property is global. Now we'll see the spotlight. Okay. So this is attenuation. So we don't want attenuation now. Okay, what makes the spotlight? So for the spotlight, we should have property like GL light F, GL light 0, GL spot direction. So by default, direction is in 0, 0, -1 direction. Anyway, if I don't set also, it would be like this. GL spot cutoff. So cutoff will make at 20 degree. So I think we have. So this is cutoff. Now the spotlight means light would behave like a torch, and this angle is 20. So 20 plus 20, this complete angle is 40 degree. That is what we are setting. Okay. So exponent we won't show now, and let's see it makes difference. So these would work in the positional light, not in the prominent in the directional one. Okay. Okay, GL light 0, GL spot direction, wrong type. So this should be a vector. Okay, so now I'm pressing positional. Oh, gone. So this is cutoff. This is a torch now. I can show the light. So this is a torch now. Okay, it reset. Now it is a torch. Okay, so only a part we can see, not the tree. When it comes to the 20 degree cutoff, then only we can see. Okay. So this is spotlight. Only part we can see. So okay. So this is cutoff. If I increase the cutoff angle, so light will be more. Initially it is ambience what it is. Okay, so we have seen the cutoff, how cutoff work. We have another property called exponent. So in the cutoff, like I have a plate where I can show the cutoff light, but it's the spotlight like a real torch, where in the middle it would be more brighter, and even it is more brighter. So this is called exponent. We can set exponent also in the light. So for the exponent, I think light source property. Okay. The way it is, so we'll bring, it will not be prominent here. So I have a file called plate.opt. So we'll add plate.obj here. So instead of tree, now we'll work on plate. Okay. Now I have another guy called plate. 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 Okay. For the plate, now we'll add one more component called exponent. Exponent is 20 right now that we are seeing, or probably less, kind of 2 DL spot exponent, and in the plate we'll see, and for that the light source will make it 1. So diffuse, specular diffuse is 1, and material will change. So we have another guy called, now we have tree, now one more will come, equal to plate. Okay, I think plate would be big here also, so we'll scale it to 0.4, something like that, and it should not emit anything, and it would be like this only, tree display. So we'll have plate display, ambience set to something, diffuse will make it purple the way the lab session is. Okay, and specular will make it 0. Okay, so we have diffuse as purple, and let's see how it throws the light. Okay, so there is a plate. I think plate is still bigger. Okay, so I think we can make it a little small. Probably 3 would work. Okay, so this is our plate, and I can show the light source, and I can rotate the plate. Okay, I'll throw the positional light now, that is a spotlight. Okay, this is positional, this is directional light. This is directional light. This is positional light. Okay, so this is positional light. Okay, so I can remove this cap, this light. Okay, so this is exponent. I mean, this is cutoff light with exponent 2. Oh, nice. Now, I can set exponent as 40 or 20, 40, let's see. Okay, so we can rotate the plate. Okay, now I can make it positional light as. Okay, it's really different. Okay, I cannot, it would, I think it will re-initialize the stuff. So there also we'll see. So it re-initialized everything. Okay, so here we'll I don't know where I am. I think I can do it again. Okay, so now we have exponent as 40. So this is 40 exponent. Okay, I'll make light position. So this is a torch, and at the center of the torch we can see the actual I can move it more. Okay, so on a plate we are focusing the torch. Now I'll change the exponent and make it less, probably 8. Okay, so I have rotated and I'll make the light positional. So not only cutoff matters, exponent also matters. See, there is a change. It really looks like a focused. So like if I have a torch in my hand and torch is now emitting light, so here it is not kind of focused, it is more focused. So this is the kind of exponent in the cutoff we get. Okay, so we'll see this point. Now we are discussing about cutoff. So we discussed, so in our lab session we had that light must fall on the vertices, and in pyramid. So in cutoff we'll see that what is the situation. So we have, so we can don't have exponent here, and just we have cutoff at 20. Okay, or we can leave the exponent to 8, and now we'll have this as so we'll make it pyramid. Let's see what's going on. Oh, so we have pyramid, and now this is the light. So we'll bring the light, this is cutoff 20. So I'll make it positional. Gone. Okay, again we'll show. So vertex must receive the light. Now I'll show the camera. I'll show the light source, and this is directional. We'll make it positional. Let's press P. Okay, so light is at vertex where it is blue. I'll move it up. Gone. Light must fall on the vertex. If I move up, it will be red. If I move down, gone completely, because vertex it is not receiving the light. I'll move left, so green is getting. I'll move right, again green is getting. Okay, nothing. So what I can do is I can remove this cut. Now it is not a cut, so it's not a spotlight. Now I'll bring the light source, I'll move it up, I'll make it positional. It's there. So vertexes are receiving light to some extent, but if I make it a spotlight, since light is coming in a kind of beam, vertices are not receiving what they should. So this is light source. I am moving it up. Now I am making it positional. Gone. So this is a kind of in vertex. I think it is called Gorward shade model. In a smooth shade model, vertex must receive. So later we will see that in Phong model, when we see the shaders programming, it's possible to have lighting on pixel wise rather than only vertex. But right now in the fixed function pipelining in Gorward light model, so this is the scenario. Now I can rotate. The way vertices are receiving the light, it is showing. Okay. I can rotate in this fashion also. If I come back to calculation of the vertex, so we have covered emission of the material, ambience, attenuation, spotlight effect, spotlight and then exponent. Then we have taken care of the light model ambience and the light source, and then diffuse, and then specular and in that shininess. Okay. So we started with light philosophy, and then we saw like all the attributes of light, like color emission and shade model, and then light model, and then diffuse, specular, and then spotlight.
If you are looking for Kiwi or machine learning training, or you are looking for Kiwi and machine learning application development, or you are looking for porting your QTQML application to Kiwi, or you are looking for 3D OpenGL application development, you can contact us. You can also sponsor our videos. Please do contact.